Thermodynamics Lecture 2. The code is TPA02. And before watching this lecture, I'm sure that you must have gone through Lecture 1, that is TPA01, in which we have seen what is the basic meaning of temperature, what is the zeroth law of thermodynamics, what is thermal equilibrium, what are different scales of temperature, and how you can convert the value of temperature from one scale to another scale. If you haven't gone through lecture 1, what I recommend before watching this lecture, better go through lecture 1, and the link of lecture 1 you can find in the description given below. Okay, now let's see what will be the objectives of the present lecture. First of all, we will see the meaning of specific heat capacity. Okay, we'll see the meaning of specific heat capacity. Then we will see the situation of problems in which the heat capacity is variable and is given as a function of temperature. Now, same in most of the problems in lower classes, you are given the heat capacity as a constant value, but in reality, it varies with the temperature. So, in conceptual problems, which call for your deep understanding and application skills, we have the heat capacity as a function of temperature, and we then need to find the value of the heat added. So, in this lecture, we will explore this beautiful skill where the heat capacity is given as a function of temperature, and we will see how we can apply the integral approach when it is given as a mathematical function, and how we can apply the graphical approach when the variation is given as a graph. Okay, so this is one of the very integral component of the present lecture, which is a very critical and conceptual point, that is a variable heat capacity. Okay, which we are going to explore in the present lecture. Then we'll see how we find the rate of absorption of heat, and then we'll come to the traditional model where you find most of the traditional or usual problems, a constant heat capacity model, and then alongside with each topic, we will be exploring the related numerical problems. Okay, so this is the roadmap, or you can say the objectives of the present lecture TPA02. Now let's see, first of all, understand what is the difference between the property of a material and property of a specimen. See, material is a substance, like suppose if I'm talking about this pen. So this pen is made of a particular plastic. So plastic is the material. And this particular pen is the specimen or object. Okay. Suppose you have a copper spoon. Okay, you have a copper spoon. So copper spoon is a particular object. Copper spoon is a particular object. And suppose you have a copper cup. So copper cup is another object, but both are made of copper, correct? So the material is same. So material is independent of the nature of the specimen or object. It is the, when you're talking about a cup, when you're talking about a spoon, so these are representing what? These are representing the specimen or the object. So when we talk about the properties, there are some properties which are the properties of the material, and there are certain properties which are the properties of the object. The property of a material or substance, these are the inherent property of the nature of the material, and is independent of the shape or size or area or mass, etc. of the object. Okay, when you're talking about the property of material, like something you're talking for copper. So if you're talking for some particular property of copper, so copper is a material. And if you're talking some material property, then that property will be same for the cup as well as for the object, like the density. Now, see, when we talk about density, many of us think, how can density is independent of the object, right? Many of us think, how can the density be independent of the object? Because we think that density is mass by volume, correct? So many of us get in the trap that density will depend on the mass. No. See, density is the property of the material, not of the object. So if you have a, say, copper cup, okay, and you have a copper spoon, both will have different masses, correct? The mass of the cup may be different from the mass of the spoon. Both will have different volume. The volume occupied by the material of copper in cup is different from the volume occupied by the material of copper in the spoon. So both have different masses, both have different volume. But since both are made of copper and density is the property of the material, so both will have same density. The density will not depend on the object. This is a very interesting thing. Many of the times the students think that density is proportional to mass. No, density can't be proportional to mass, because in proportionality, when you write something is proportional, suppose you're writing x is equal to y by z. When you can say x is proportional to y, when you can say x is proportional to y, you can say x is proportional to y only when z is constant. Then only you can say x is proportional to y. Otherwise, you can't say that x is proportional to y if z is also changing with the change in y. Correct? So when you are changing the volume, the mass is also changing. Say the spoon has different volume, different mass. The cup has different volume, different mass. But the density of copper will remain the same. The density of cup will be m1 by v1, and the density of spoon will also be rho, that is m2 by v2. So mass is changing, volume is changing, but the ratio of mass and volume is not changing. That is the density. So density is basically the property of the material, not of the property of object. This is very critical and point to understand, that density is not the property of the object, it is the property of the material. If you are changing the mass, the volume will change, but density will not change. So whenever we have some property of a material or substance, that is the inherent property, and this property will not depend on the shape or size or area or mass of the object. You can make any object of the same material. This property will not change. Correct? When you talk about the property of a specimen means particular object. Like cup is a specimen. Okay? Your spoon is a specimen or object. So that particular specimen is a property of a particular sample of material and may depend on the specific parameters of the object. So when you are talking about the property of particular specimen, particular object, then that property depends on the parameters or properties of that object, like mass and volume. We have seen this spoon will have different mass and the cup will have different mass. The spoon will have different volume and the cup will have different volume. So you can see the mass and volume are basically the properties of the particular object, not of the material. Okay. Suppose we have different pieces of gold, all of 22 carat. Okay. Now, if you see there are different coins of the gold, there are different biscuits of the gold. What do you think? Can I say, irrespective of knowing the volume, even if I don't know what is the volume of the coin, what is the volume of the biscuit, I don't know. Even I don't know the masses, but still, can you say the density of each of the specimen or material will be same? Yes or no? Yes, because density is the property of the material. And when you're talking about the gold of same carat, 22 carat, so they will have the same density. Of course, they are different specimen, they are different objects, so they will have different masses, they will have different volumes, but the density will remain the same. So this is how we got the meaning. What is the difference between property of a material or substance and the property of a specimen or object? Now let's see what will be the role of the heat. When you supply heat to some sample of substance, then what role it will play? See, heat can play its role in two classes. It can raise the temperature of the substance. It can raise the temperature of the object. Suppose you have a cup of copper, correct? And you're giving some heat to the cup of copper. So the temperature of the cup is increasing. The state of the cup, that is the solid state, is same. Only the temperature is increasing. So one role of the heat is to raise the temperature of the sample of substance. Got it? One role is to raise the temperature of sample of substance. Now let's see what will be another role of heat. The heat can also play its role in changing the state of the object or material. State means phase or state means like solid, liquid, gases. These are the three major states or three major phases. So suppose you have a cup of copper in the solid state and you keep on supplying the heat, the temperature is keep on increasing. Ultimately, it will reach to its melting point and the solid state will start converting into liquid state. Okay, so this will be the change of state, and when the change of state will be taking place, there will be no change in the temperature. So whole heat coming is utilized in changing the state. This we will explore later in more depth, in more clarity. For the time being, we just are focusing what are the two major prime roles of the heat. So one role is what? To raise the temperature of the sample, and when it is raising the temperature, it is not changing the state. And another role is what? To change the state or phase of the substance without changing the temperature. So these are the two major roles that the heat plays when you give it to any sample of the substance. Now let's see one very critical point which forms the basis of lot of articles we are going to face ahead. The amount of heat needed to raise the temperature of a substance of given mass by the same amount is not same at different temperatures. The amount of heat needed to raise the temperature of a substance of given mass, means same mass, by same amount is not same at different temperature. Let's see it in more clarity what it means. Say, suppose we have 1 kg of water, okay? Suppose we have 1 kg of water and you want to raise the temperature, say, from 15 degrees Celsius to 16 degrees Celsius, and then you want to raise it further, say from 31 degrees Celsius to 32 degrees Celsius, okay? So say, in this case, you are raising the temperature by 1 Celsius degree, correct? And again, in this case, you know, we have seen in lecture 1, when you're writing the change in temperature, we write Celsius dead degree. And when you are writing the absolute temperature or the value of particular temperature, then we will write degree, then Celsius. We are writing the change. So again, you are changing the temperature by 1 Celsius degree. So in both the cases, you can see, in both the cases, the mass of water is same, given mass. You are raising the temperature by same amount, 1 Celsius degree, 1 Celsius degree, but the heat required will not be the same. Suppose here the heat needed is Q1 and here the heat needed is Q2. So Q1 will not be equal to Q2, okay? So this is a very critical point. The heat needed to raise the temperature by same amount will not be same at different temperatures. It will depend on the initial temperature, okay? Note it down. Now see, suppose we want to raise the temperature of 1 gram of copper by 1 Celsius degree, okay? And from 15 degrees Celsius, we want to raise by 1 Celsius degree. And when you are raising it from 15 degrees Celsius to 16 degrees Celsius, the heat needed is Q2. And when you are raising it from 25 degrees Celsius to 26 degrees Celsius, the heat needed here, the heat needed is Q1, and in this case, it is Q2. So from 15 degree to 16 degree, heat is Q1. From 25 to 26, heat is Q2. Now, see, in both the cases, the mass remains the same. It is 1 gram of copper. And in both the cases, you are changing the temperature by the same amount. So what do you think? Which option will be correct? Q1 will be equal to Q2. Q1 will not be equal to Q2. In both cases, the temperature change is same. None of the above. Of course, more than one option may be correct. Suppose it is multiple correct, one or more option will be correct. So absolutely, option C is the correct option, surely, because in both the cases, the temperature change is same. And Q1 will not be equal to Q2. Right now, we have seen even when you're changing the temperature by same amount, but heat needed will not be same. It will depend on the initial temperature. So Q1 will not be equal to Q2. Okay, so the correct options will be B and C. Now let's see what is the definition of 1 calorie. So we define 1 calorie as the amount of heat required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. It's 15.5 degrees Celsius. This is the definition of at a standard pressure. This is the definition of 1 calorie. You cannot simply say that 1 calorie is the amount of heat needed to raise the temperature of water by 1 Celsius degree. No, you also need to define what is the initial temperature and what is the final temperature. Because as you've seen, the temperature heat needed to raise the temperature from 14.5 degree to 15.5 degree Celsius will be different if you're raising the temperature of water, say from 20 degree to 21 degree Celsius. So when you're defining what is calorie, you also have to define what is the reference level for the initial and final temperature. So this is the standard definition of 1 calorie. Now let's see what is the meaning of specific heat capacity, or simply the specific heat denoted by small c. First of all, understand it is the property of the substance or nature of material. It is not the property of the specimen, okay? It is the property of the substance. So we always say something like this: a specific heat of water, a specific heat of copper, a specific heat of aluminium, correct? We never say, we always associate a specific heat with the material, with the substance, not with the object. We never say a specific heat of beaker. No, we never say sentences like this: a specific heat of beaker. Never. A specific heat of rod. Never. Because beaker and rod, all these are objects, and specific heat is the property of a substance. It means what? If you have a rod of copper and if you have a cup of copper, can we say both will have the same specific heat? Yes or no? What do you think? Will both have the same specific heat? Yes, because both are made of copper, and specific heat is the property of substance. Now let's see what is measured by specific heat. It measures the amount of heat needed to raise the temperature of unit mass of a substance by unity. So basically it measures how much heat is needed by the substance. Suppose we have a substance of mass m, okay, and you are raising it temperature by amount dt, and the amount of heat needed is dq. We are taking infinitesimal amount because the heat needed will depend on the initial temperature, so the heat required will not be the same as we have seen right now. So we define the specific heat as small c, the heat needed dq, per unit change in temperature dt, per unit mass m. So this is the formula for specific heat. Now what will be the SI unit of a specific heat? The SI unit will be heat as a unit of joules per kg Kelvin. And the change in temperature, when you're writing the change in temperature in Kelvin, it will be the same as the change in temperature in degree Celsius. So you can also write joule per kg per Celsius degree. These two values will have the same magnitude. So if you are given the specific heat as something like x joule per kg Kelvin, it will be same as x joule per kg Celsius degree. Got it? Because the temperature change is same in Celsius degree or Kelvin. So this is the formula for specific heat. dq by mdt. dq is what? The infinitesimal amount of heat which is absorbed by the substance. M is what? The mass of the substance. And dt is what? The change in temperature. If you are making conversely, if you are making dq as the subject, so dq will come to be mc dt. dq is giving you the small amount of heat which is needed to change the temperature by dt, so it will come to be mc dt. Okay, so you can write the formula for specific heat, and it measures the amount of heat required to raise the temperature of unit mass of substance by unity. Now tell me one thing, just think what you have learned till now. The specific heat of a substance is variable with temperature. True or false? Think. It's saying the specific heat of the substance is variable with temperature. It means the specific heat will change with temperature. So what do you think? Is it true or false? Write your answer and the region. Just make the video still for 1 minute in your notebook. Write your answer and the logic behind it. If you're writing true, write the logic behind it. If you're writing false, write the logic behind it. And then resume the video. Now, see, the answer is what? The answer is true. Because we have seen what is the specific heat. So, specific heat is basically the amount of heat needed to raise the temperature of unit mass. Unit mass means 1 kg by unity, say 1 Celsius degree. And today we have seen if you are changing the temperature by the same amount, say 20 to 21 degrees Celsius and say 30 to 31 degrees Celsius for the same mass of the same material, then the heat needed is not same. And if the heat needed is not same, so of course the specific heat at 20 degrees Celsius will be different from the specific heat as at 30 degrees Celsius. So basically, precisely, specific heat varies with temperature. That is, precisely, specific heat varies with temperature, okay? Because the amount of heat needed to raise the temperature of same amount of substance by 1 Celsius degree is different at different temperature. We can find the heat added to any system, okay? So suppose we have a system and at a particular instant you have given it a heat dq due to which the temperature got a change, say dt, and the mass of the system is m and the specific heat is small c, okay? So we can write dq as what? So we have seen mc dt, correct? This is the value of dq. Now dq is basically giving you an infinitesimal amount of heat. Infinitesimal amount of heat, a very small amount of heat in common language, to change the temperature by dt. Now, if you are changing the temperature from, say, we are changing the temperature from T1 to T2, and total heat needed is capital Q. So we will apply the concept of integral, correct? Capital Q will be the summation of dq, and in language of calculus, summation means integral. So it will be mc dt. So this is the generalized formula for finding the heat given to the system. It will be mc dt, correct? So this is the formula for the heat absorbed by the system. Now the point is, what are the parameters which can be taken out of the integral? So if you are assuming that mass is constant, when the temperature is changing, there is no change in the mass. So m can be taken out and it will be c dt from temperature 1 to temperature 2. Now we are not bringing c outside, mind it, because as I told you, the specific heat varies with temperature actually. So if you're taking c outside, you're taking some special case model. Right now we are not going for that special case, okay? So we are not bringing c outside, we are taking the c inside the integral. It depends what is the value of c in terms of the temperature. So this is the formula for finding the heat added to the system. And you know, as I told you in lecture 1, in our convention, in our model, Q will denote heat added to system, okay? So if Q comes to be positive, heat is actually added, that we have seen in lecture 1, and if Q is negative, it means heat is actually lost. But our convention will be heat added. Whenever we will write Q, Q will denote the heat added. So Q can be positive or Q can be negative, depending what actually is happening. So we are taking one convention, what is the heat added to the system or heat gained by the system, that is M integral of C dt. Got it? So this is the formula for finding the heat gained by the system in terms of the specific heat and change in temperature. Now see, illustration 1. First of all, we will see those problems in which the specific heat will be given as a function of temperature. As I told you in the very beginning, these are very conceptual and critical problems because in most of the cases of lower classes, C is a constant function. It doesn't given to be vary with temperature. And even in present lecture also, present scope of syllabus also, you will meet a lot of problems where C will be constant, but problems will also be made in which C will be a variable like this. The specific heat of a substance depends on the temperature as C bracket T. C bracket T means what? C as a function of temperature, 2T plus 3T square joule per kg Kelvin, where T is the temperature in Kelvin. Find the heat needed to raise the temperature of object of the substance of mass m naught from 200 Kelvin to 210 Kelvin. Okay. So let's see how we will proceed with the problem. So we are given the specific heat as a function of temperature as what? 2T plus 3T square joule per kg Kelvin. So clearly you can see the specific heat is given as a function of temperature and mass is m naught, and we have to find the total heat. So we know the formula. If m is constant, it will be outside. It is C dt from T1 to T2. Now what do you think? Can you bring the specific heat outside the integral? No, we can't bring it out. Why? Because it is a variable. It depends on the temperature. So for solving the integral, we must have C as a function of temperature, and that is given in the problem. So we'll have C as a function of temperature dt m naught from T1 to T2. So let us put what is given. So it implies that Q will come to be m naught. Let us put the expression of C, 2T plus 3T square dt from T1 to T2. And what are the limits of T? 200 Kelvin to 210 Kelvin. And what are the parameters given in the problem? We have to keep T in Kelvin, okay? And specific heat is given in joule per kg Kelvin, okay? So let us integrate. So we'll get m naught 2T square by 2 plus 3T cube by 3. Put the limits of integral. So I have T1 200 Kelvin and T2 as 210 Kelvin. Now 3 will get cancelled away and 2 will get cancelled away. So you will get Q is equal to m naught T square plus T cube within the limits 200 to 210. So we'll get m naught 210 square minus 200 square. We are putting the limits plus 210 cube minus 200 cube. So you can solve it. What will be the value? So we'll get 210 square minus 200 square. So we'll get it implies that Q will come to be m naught. You'll get 4100 plus you'll get 210 cube minus 200 cube. You'll get 1261000. So you'll get m naught 1265100, and answer will be joules. This is the value of heat needed. That's all simple mathematics. The point is that the approach, how we are finding the integral and how you are not taking out the value of c, because c is a variable in this case. Okay, so this is how we did this problem by the integral of m integral of c dt, and we are not bringing c out because c is given as a function of temperature. Got it? Okay, now let's move to the next problem. Suppose the specific heat capacity of a substance is a function of temperature. Again, you see the similar problem is there for your practice, where T is the temperature in Celsius. So given here, C is the temperature, T is the temperature in Celsius. What is the heat energy required to raise the temperature of 2 gram of the substance from 5 degrees Celsius to 15 degrees Celsius? So again, you can see here it is given S. Sometimes, standard notation for the specific heat is C, but often in some problems we are given the value of S. That's why in this problem particularly I've given S. So make you acquaintance with the notation. Sometimes S is also given. You can write a C in integral, no problem. So heat will be what? Mass can be taken as a constant factor. C or S, whatever you want to write. dt from T1 to T2. C will not come out. And what is C? We can write it simply C, specific heat, 0.20 plus 0.14 T plus 0.023 T square with dt from T1 to T2, and T we have to put in Celsius, and it is given what are the range where we have to increase the temperature, that is 5 degrees Celsius to 15 degrees Celsius. Now it's a straightforward integral, and mass it is given in gram. So mass you have to keep in gram, do not convert it in kg, and it is given how much? It is given to be 2 gram. So simply put m to be 2 gram, and it's straightforward integral. It will be 0.20 t, 0.14 t square by 2, 0.023 t cube by 3, and put the limits of t and check out the answer. 4 options are given. I'm leaving it for your self-evaluation. Check it out which option will come to be correct. Okay, it's simple, straightforward, simple integral and putting the limits. Got it? So we have seen 2 problems in which the heat capacity is not constant but is given as a mathematical function of the temperature, and we have seen in how in such problems we proceed for finding the heat absorbed by the object. We simply integrate, m is taken outside, mass being the constant, and then we integrate c with dt. Now let's see again the variable heat capacity, but now in a different approach, the graphical approach. So suppose you are given the variation of heat capacity with temperature, and some graph is given. Okay, now we are not given the mathematical function, but some graph is given, and we have to find what is the heat absorbed between 2 particular temperatures, say T1 and T2. So if you go to the basic mathematical equation, so Q came to be m c dt, correct, from T1 to T2. And we know from the starting of mathematical tools in class 11th that integral means area of the graph. So this thing is giving you what? This is giving you area of small ct graph, correct, between T1 and T2. So if you have to find what is the heat absorbed between the temperatures T1 and T2, make 2 vertical lines corresponding to the values of T1 and T2. Take the temperature axis and the graph and take the bounded area, this area. Okay. So this area will give you this thing. So the heat absorbed will be the mass multiplied by the area. Got it? So this is how we can find the heat from the area or graph of specific heat versus temperature. This is also very important concept. Okay. Now, see, let's see one or two illustration on specific heat graphical interpretation. Suppose the variation of the specific heat of a substance with the temperature is given below. So suppose I'm giving you one graph. Okay. And this is how it's starting from. Okay. And here you are given the value of C, specific heat, in the unit of joule per kg Kelvin. And this axis is the temperature, say Kelvin. And we have to find what will be the heat needed. Suppose these values are given as 20 Kelvin, and this is given 50 Kelvin, and this is 100. Okay. And we have to find what heat is needed, and say the mass is given to be m naught. Okay, it is given. We have to find what will be the heat needed to raise the temperature from 20 Kelvin to 50 Kelvin. And you're given the graph. So we have seen the heat needed. Q is the heat, is mass multiplied by the area of the graph. Now, area we have to take between the temperature limits, the graph, and the temperature axis. So it's basically a rectangle. Area will depend on the geometric figure. It may be trapezium, triangle. Here it is rectangle. The sides are 30 into 100, and mass is m naught into 30 into 100. So it is 3000 m naught. And what will be the unit? So everything is in SI. The unit will come to be in joule. Okay. So this is the answer for this particular problem. Okay. Now let's see what is the rate of heat absorption. Sometimes in the problems or in the articles, we have to find or relate the rate of heat absorption. So rate of heat absorption is it means dq by dt. T here means the time, how heat is getting absorbed with respect to time, the time rate of change of heat. And if you're writing dq as mc dt, we have seen this is the basic equation. And if you divide by dt on both sides, so the rate of heat absorption will be mc dt by d small d. And this is what? This is the rate of temperature. How temperature is changing with time. Rate of change of temperature, of course, with respect to time. Okay. So you got the formula, the rate of heat absorption is equal to mass multiplied by heat, specific heat multiplied by the rate of change of temperature. Now you can given the values ki how the rate of change of temperature varies. If in a particular case, say rate of change of temperature is constant, if dt by dt is given to be constant, that is a special case, say k. Okay. So in such a case, you can write the rate of absorption of the heat is m into c into k. Now m is a constant, mass is not changing, k is also a constant. So in this case, you can write the rate of absorption of heat is directly proportional to specific heat. This is a special case when your rate of change of temperature is constant with time. So this will become constant. And if we're putting a constant here, constant multiplied by constant will be a constant. C may be variable with temperature. So in such a case, the rate of change of heat will depend directly proportional to the specific heat. And if specific heat is also constant, so this will come to be a constant. It depends on the nature of the particular problem. Okay. So this is how we find the rate of heat absorption. Now see the next problem. That's very beautiful problem. In the given figure, we have the variation of a specific heat capacity of a solid as a function of temperature. The temperature is increased continuously from 0 to 500 Kelvin at a constant rate. See, there's some information is given, okay? The temperature is increased from continuously from 0 to 500 Kelvin at a constant rate. What it means? It means the rate of change of temperature with time is constant. Just say K. This is something the problem is telling, a very critical point, okay? Ignoring any volume change, choose the correct statement or statements. The rate at which heat is absorbed in the range 0 to 100 Kelvin varies linearly with temperature. Heat absorbed in increasing the temperature from 0 to 100 Kelvin is less than the heat required for increasing the temperature from 400 to 500 Kelvin. There is no change in the rate of heat absorption in the range 400 to 500 Kelvin. The rate of heat absorption increases in the range 200 to 300 Kelvin. Now see, out of the 4 options, 3 options involve something related to the rate of heat absorption. Okay? Except option B. Option B is related to the heat absorbed, and option A, option C, and option D, they deal with the rate of heat absorption. So first of all, let us study about the rate of heat absorption. This is the variation of the specific heat with the temperature. Can you see? And you can see from the graph, the specific heat is not constant with temperature. It is increasing with temperature and not linearly. The specific heat is increasing with temperature in a curvilinear way, and then it becomes constant over 400 Kelvin. And in the problem, it was given that the rate of change of temperature with time is constant. That was given in the problem. Say K, we have written this thing. And right now we have seen today how we can find the rate of absorption of heat. So this is mc dt. So therefore dq by dt will be mc dt by d small t. Now in the particular problem, this quantity is given to be a constant. That is, the temperature is changing at a constant rate, say K. So therefore, the rate of the heat absorption will be mck. Now we can write m into k. These are the product of two constants. So it will be a constant. So you can write dq by dt is say ak, where, sorry, ac, where a is a constant, correct? And C is what? Specific heat. We cannot take this product as a constant because the specific heat is changing with temperature. So when the specific heat is changing with temperature, see, A is a constant, correct? A is the product of two constant, which is given the name A, m into k. So since C is changing with temperature and dq by dt is AC, so therefore rate of absorption of heat, that is dq by dt, it will also change with temperature. Yes or no? Because it depends on C. It is directly proportional to C. Can you say A is a constant? So you can surely say that rate of absorption of heat is directly proportional to C. So if C is changing with temperature, so surely the rate of absorption of heat will also change with temperature in the same manner as C is changing. Now let's see the options. And you can write the rate of absorption, that is the rate, is directly proportional to C. correct? Because A is a constant. So if C is changing linearly, the rate of absorption will also change linearly. If C is constant, the rate of absorption will also be constant. If C is increasing exponentially, the rate of constant will also increase, rate of absorption will also increase exponentially. So the rate of absorption will have the same behavior of change as the behavior of C, specific heat. Now let's come to the option. We have done the analysis. Now let's come to the options. Option A, the rate at which the heat is absorbed in the range 0 to 100 Kelvin varies linearly with the temperature. So see, if you see from 0 to 100 Kelvin, this is the value of 0 and this is the value of 100 Kelvin. So we have seen the rate of absorption varies in the same manner as the variation of C. And from 0 to 100 Kelvin, C is varying in a curvilinear way. It's a curve, not a straight line. So it is saying the rate at which heat is absorbed in the range 0 to 100 Kelvin varies linearly with temperature. Absolutely, this is incorrect. Yes or no? It is not changing linearly with temperature. It is a curvilinear graph. Okay? Heat absorbed in increasing the temperature from 0 to 100 Kelvin is less than the heat required for increasing the temperature from 400 to 500 Kelvin. Now, when you want to know how much heat is needed, we take the area of the graph. So this will be the area from 400 to 500 and this will be the area from 0 to 100, correct? So obviously this area is more than this area. So here more heat is needed. So this option is correct. There is no change in the rate of heat absorption in the range 400 to 500 Kelvin. Now see, again, we are coming to the rate of heat absorption. So it will depend on C, how C varies. So from 400 to 500 Kelvin, you can see C is approximately constant. Can you see this axis is the asymptote of the graph? So it is approaching a constant value. So from 400 to 500 Kelvin, C is approximately constant. And if C is approximately constant, so your rate of absorption will also be approximately constant. So this option is also correct. The rate of heat absorption increases in the range from 200 to 300 Kelvin. Now, what about 200 to 300 Kelvin? So this is your 200 Kelvin and this is your 300 Kelvin. Again, we are talking about the rate of absorption, so we will focus on the behavior of C. So you can see C is increasing. C is increasing, though it is increasing in the curvilinear way, but that doesn't matter. It's simply about the increment. So from 200 to 300 Kelvin, C is increasing. And if C is increasing, so your rate of absorption will be increasing. So option D is also the correct option. Okay. So except A, all three are correct option. Had it been a linear graph, here, something like this, a straight line, though it is not a straight line perfectly, it is curvilinear, though slightly curvilinear, but it is curvilinear. Had it been a linear graph, then option A would also have been correct. That is from 0 to 100 Kelvin, rate of absorption would vary linearly, but it is curvilinear. Okay, so this is also a very beautiful problem in which you have seen the graphical interpretation of the heat absorbed, the graphical interpretation of the variation of C with temperature, the graphical interpretation of the rate of absorption of heat with temperature. Okay. Now let's see. Till now we have seen very practical cases where the specific heat varies with the temperature. Now we will come to one ideal case, a assumed model, a prototype, in which we will assume that the temperature range we are talking about, here the specific heat is taken as constant. That is a hypothetical model. We know actually the specific heat varies with temperature, and we have seen how to solve such problems both by integral method as well as by graphical method. Now we are coming to the traditional case, a special case, when we have a constant value model of specific heat. And most of the problems in usual competitive examinations or standard examinations will involve this model. Unless stated otherwise, note it, unless stated otherwise in the problem, you will assume that the specific heat is constant. You will take this ideal model. Okay? And if something is given as a temperature of T, like in the previous cases, or as a graph, then we'll go for such cases. Otherwise, we will assume C is constant. So see, in this case, what equation you'll get. So we will start with this thing where we have seen. Now, in this special case, C is constant. We are taking a model in which C is constant. So what you will have, Q will come to be M. Now C will come out, and you will have dt from T1 to T2. So Q will come to be MCT from T1 to T2. So we'll get MC T2 minus T1, and T2 minus T1 simply you can write delta T. So you'll get MC delta T. So this is the formula for the heat absorbed for constant C model. Constant C model. Okay. And whenever you are applying this formula, be careful about one thing. Delta T will be taken as final temperature minus initial, never higher minus lower. Always this thing. So delta T can be positive or delta T can be negative. If delta T is positive, your Q will come to be positive. If delta T is negative, your Q will come to be negative. Clear? Number one. Number two, Q denotes the heat absorbed. We never talk about heat lost. We will talk about heat absorbed or heat gained by applying this formula. And delta T will always be taken as final minus initial. So if Q comes to be positive, already I told you, it means the heat is actually gained. If Q comes to be negative, it means heat is lost. Okay. So always follow this convention. We need not to worry about whether the heat is lost or whether the heat is gained. We are taking a model in which we are talking about the heat gained by the body. Either Q will come to be positive or Q will come to be negative, depending on the relative values of TF and TI. So as I told you, the convention we are taking, we always apply when we have a constant value model of a specific heat. Q will be mass multiplied by specific heat multiplied by delta T, MC, and this is final temperature minus initial temperature. And this will denote what? The heat gained by the system or heat added to the system. Okay? So you need not to worry whether Q will come to be positive. No, suppose, example, suppose Q comes to be 75 joule. Now Q is coming to be positive, and your model is the heat gained. What it implies? It implies that heat gained is 75 joule. Okay. Now suppose in some particular numerical problem, you got a value of Q as minus 45 joule. Now you're getting a negative value. And in your model, Q is the heat gained. We never talk about heat lost. We will always talk about heat gain. So basically your heat gained is minus 45 joule. That is what you are getting. So what it means, the heat lost is, of course, heat lost is opposite to heat gain, so 45 joule, not 75, 45, correct? So here the negative sign, when Q comes to be negative, actually heat is lost. But you at the very first place, you need not to worry about it. You will always apply this equation, the equation of heat gain, MC delta T, and delta T will be final minus initial. Itself, it will give you a positive value of Q or negative value of Q. So we'll always talk about heat gain. We never talk about heat lost. Like in lower classes, when you do the calorimetry problem, you write something like that. Heat gained by one body will be equal to the heat lost by another. Now we won't say heat lost. We'll simply talk about heat gained by everybody. Okay. And of course, in an isolated system, every body cannot gain heat. Some object or body must be losing the heat. So if there are two objects and you're talking about the heat gain for both of them, so one may have positive Q and one may have negative Q. One will actually gain heat, it will have positive Q. And the one that will be losing heat will have negative Q. But our Q will represent heat gained. If you have any doubt, any problem, you can contact me. My numbers are given below on the display. You can see both the numbers. You can send me WhatsApp. Okay, I will send you whenever, if in any lecture, in any problem. If you have any doubt, you can always contact me. So see the supply of electrical energy. Suppose we have a heating coil of 2.40 kilowatt. We know the unit of power is watt and kilo means 10 power 3. So suppose you have a heating coil and here the electrical energy is coming. So the energy will be P into T, correct? So its power is for 2.40 kilowatt. So what will be the work done or energy supplied? The work done or energy supplied by the coil in time T. So work or energy will be either you can write work or energy P into T. So P is what 2.40 kilo means 10 power 3 into T, correct? So this is something very basic which you must have done in lower classes, correct? This is how we will find the work done by the electrical energy which is being supplied. Actually, what I made a recap because this thing is going to be used in some of the numerical problems of thermodynamics. Now let's see the principle of conservation of energy. Suppose we have a system. Suppose we have some system, okay? And it has some kinetic energy K, potential energy U, okay? And there are different objects in the system, and the total heat gain in the object, total heat gain, again, see, I'm talking about gain. I'm not talking about loss. I'm just talking about gain. The total heat gain is sigma Q. And the external work or energy supplied is WEXT. So by conservation of energy, you can write the change in the kinetic energy plus the change in the potential energy plus the total heat gained by the objects within the system. These are the system energy transfer is equal to the total work done by all the external agents. This is simply the conservation of energy you have studied in work energy, where we have done lots of problems. In that, we used to write only the mechanical energy delta K and delta U. Now also there is third term which is involving the heat gained by all the objects within the system. Heat gained by all the objects within the system. Okay. If the system is isolated, there are some special cases. If the system is isolated, see, number one. So if the system is isolated, so we know in work energy, we have seen the net external work will be 0. So in this case, delta K plus delta U plus the net heat gain will be 0. This will be the equation. Okay. Now another special case. If there is no change in the kinetic energy and no change in the potential energy, so your conservation of energy will give the equation the net heat gain is equal to total work done by the external agent, correct? These are simply the special cases of this generalized equation. If the system is isolated, the external work will be 0. If there is no change in the kinetic energy and potential energy, then LHS will have simply the net heat gain and RHS will have the total work done. Okay. As we will be doing the problems, this equations application will become more clear. Okay. Let's see some of the problems. An object of mass 6.5 kg falls through a height of 50 meter and by means of a mechanical linkage rotates a pedal which that stirs 520 gram of water. The water is initially at 15 degrees Celsius. What is the maximum possible temperature rise? See, here the keyword is maximum possible temperature rise, and you are given the specific heat of water. Okay. So basically, we have water How much? 520 gram. And you are releasing an object U0 from a height of 50 meter, and there is a mechanical linkage which is rotating the pedal, okay, which is rotating the pedal, which is stirring this 520 gram of water, and the initial temperature of water is 15 degrees Celsius, and you have to find what can be the maximum final temperature. The keyword is maximum. So see, now for the maximum possible temperature rise, we will take some assumptions. For maximum possible temperature rise, first assumption we will take, there is no loss of heat. No loss of heat. Okay. To surroundings of beaker or to the object itself. That is, all heat is gained by water and nothing else. There is no other heat transfer. Now, for conservation of energy, we know we have to define a system. So I'm taking the system as the object plus water, object that is falling plus planet. And since you're taking planet in the system will have gravitational potential energy. This we have seen in work energy. So what will be the change in the gravitational potential energy minus mgh? M is what? Mass of object. I'm writing mo. What is the change in kinetic energy? 0, because we are taking initial kinetic 0. It's being released, so initial velocity will be 0. And final kinetic is also taken as 0 because we have to find the maximum rise in temperature. So we will assume that the object, after being dropped, comes to rest. It won't have any kinetic energy. All the energy will be transferred in the form of heat to what? To the water. So delta K will be 0. And what is the net heat gain? So the only substance which is gaining the heat is water. And the formula will be mass of the water, specific heat of the water, delta T. So mass of water, specific heat of water, final minus initial. Now there is no external agent in this problem. So the total work done by the external agent will be 0. Now gravity won't be counted as the external agent, we know. We have seen so many times in work energy. Now you have taken planet in the system. So gravity is playing the role in the gravitational potential energy, not in the external work. Okay. Now apply the conservation of energy. So by conservation of energy, you will get change in potential, change in kinetic, plus the net heat absorbed by all the components of the system is total work done by the external agents. So delta U is minus mass of the object, GH, and delta K is 0. And this is what? Mass of the water, the specific heat of water, final minus initial is equal to 0. So you'll get, therefore, TF minus TI. Now this will come on this side. You'll get M naught GH divided by mass of water into specific heat of water, correct? So what will be the final temperature? So your final temperature will come to be how much? You'll get M naught GH divided by mass of the water, specific heat, plus the initial temperature. Now all this data are given in the problem. All these data are given in the problem. You can simply put these values. Your given specific heat is 4190 joule per kg Kelvin. Initial temperature is 15 degrees Celsius. Height is 50 meter. Object has a mass of 6.5 kg and water has a mass of 520 gram. So you can simply put the values. You will get the answer. It's simple maths, straightforward calculation. Okay. Put the values and you will get the answer for the final temperature. Okay. Now see the next illustration. A small electric immersion heater is used to boil 136 gram of water for a cup of instant coffee. The heater is labeled 220 watts. So we have a small heater, and of course there is some heating element, and it is given 220 watt. Calculate the time required to bring this water from 23.5 degrees Celsius to the boiling point, ignoring any heat losses. So say here what is happening. Here the electrical energy is doing work, yes or no? Electrical energy is doing work, and the work done, you can call it an external work, will be P into T, correct? Number one. And the heat will be absorbed by the water. So the initial temperature is 23.5 degrees Celsius. The final temperature, we have to bring it to the boiling point, that is 100 degrees Celsius. You are given the specific heat of water. The change in temperature will be final minus initial. So you'll get 100 minus 23.5 Celsius degree. And same thing will come to be in Kelvin. Remember, the change in temperature in Celsius degree and Kelvin is the same. Change in temperature. Now, what will be the heat absorbed by water? So let's say mass of the water is specific heat of water into delta T. So mass of water is given, specific heat is given, and you can put Tf minus Ti this value. So you'll get this value, Q of water. Now there is no change in the potential energy, no change in the kinetic energy. So by conservation of energy, you will get LHS will come to be simply the net heat absorbed by the components of the system. RHS is total work done by the external agent. So this will come to be heat absorbed by water, because water is the only component which is absorbing the heat, and this is the work done by electricity. So you will get mass of the water C, final temperature minus initial temperature is P into T. Now make T as the subject, you will get the answer, mass of the water, specific heat, final temperature minus initial temperature divided by P. So this will be your answer. Put the values, you'll get the answer, straightforward calculation. Okay. So this is the approach for solving such problems of heat transfer. So that's the end of your lecture TPA02. Now let's see, have some idea for the upcoming lecture TPA03. In TPA03, we will see, today we have seen the meaning of specific heat, which is the property of material of the substance. In the next lecture, we will explore the topic of heat capacity, capital C, which will be the property of not the material, but particular object. Like we say specific heat of copper, specific heat of water, but when we talk about heat capacity, we say heat capacity of beaker, heat capacity of rod, heat capacity of coin, because that is the property of the object. Then we'll see the related numerical problem with heat capacity, and problems involving then both heat capacity as well as the specific heat. Then we'll see the heat of transformation when the state gets changed from solid to liquid or liquid to gas. Then what changes take place, that is concerned with the heat of transformation, and of course the related numerical problems. The same thing after going through this lecture, for the optimum performance, make the lecture notes, clear your doubts. Okay, then solve the DPP of this lecture, TPA02. You have to solve the DPP and then attempt the minor test for TPA02. So these are the 4 steps for extracting out the optimum